So this is a talk on replication and sharding. So this is really just the basics of how replication works, how you can think about it compared to MySQL, and then just a general overview of how sharding works and ways to think about that. So my name is David Murphy. I am the practice manager for MongoDB at Percona. But before that, I was one of the original Mongo masters in the community for Mongo, as well as the former lead DBA at ObjectRocket, which was the high-performance database as a service for Mongo. Well, actually, it still is. It's run by Rackspace. But before even that, I've spent 15 years in MySQL. I started with MySQL 3.22, and I made the very scary transition from RDBMSs to NoSQL as a result of being told to at EA. It's a little terrifying. Okay, this looks better. So what I wanted to cover is the Mongo architecture first, just how it looks, how it's made up, and then what oplogs are and what journals are in Mongo and how they work, and then going into how replication works, like what does a secondary node do to get a piece of data from a primary node. I'm following that up with some special settings that exist in Replica Sets on ways you can manipulate the way HA works, but also the way you can delay replication on a specific node for backup nodes or hide them to do special job flows on them, which is a little bit harder to do in the MySQL world. And from there, I can talk more about like config servers and how those operate. Think of those as a metadata repository for sharding. And the sharding will use that to figure out where a piece of data should exist. And then in that, I'll explain what a chunk is, because it's a logical unit that Mongo uses to move things around and keep your system balanced. Think about it like if we were doing a modulus-based sharding in MySQL through your application, you might have 10 shards, and in those 10 shards, 10% of your users exist in each of those. But if in one range of those users, all of a sudden you have a lot more users or a lot more activity, it's very problematic in that design pattern to actually rebalance the data. And using smaller chunks, Mongo allows you to rebalance that data more online. And then I wanted to go over a couple key rules to kind of follow when you're thinking about a shard key that will really trip a lot of people up most of the time. And then also just from an operational perspective, how can you tell what type of automatic operations Mongo has done on your behalf so that you're not just blindsided when somebody says, hey, this is broken, you know where to go look to find those problems. So the main architecture is pretty simple. As you can see, you have a public cloud and you have your app nodes, and this graph isn't really super clear on this projector, but in the app nodes, you would also put a MongoS node, which think of it like a router or a MySQL proxy with a lot of fanciness to it. And that will then talk to a config servers to understand what the map of your data set looks like, and then could route it to one of those two shards in this setup. And in each shard, what you do is you have 3 nodes or however you've configured it that automatically fail over to one another, so that if I was querying a MongoS and I had an election on my read from shard 1, I could reissue that read again, and I would automatically get the new primary that was selected and get my data. And so it makes it very easy in some of the drivers to literally set a flag that says retry on error, and then boom, your your application flow would automatically retry that, or after several failures would it finally error to the user. So it helps prevent users from, they'll notice a slightly slower response from the database, but they'll still get their page. And so that's usually much better and considered degraded versus down. So in Mongo, what you have is a single node would just be a single MongoDB process. And a single server in some design patterns for Mongo actually would have multiple MongoDB processes running on them, because up until 3.0, you could really only use 2 cores effectively. And after that point, what you needed to do is add more nodes and put them on different NUMA zones or something like that so that you could get more effective use of your hardware. Starting in 3.2, WireTiger is now the default engine. And obviously, Percona has our build that has fractal trees and RocksDB, which you heard about in Mark's keynote today. And in those can all use many more CPUs, but still, to Mark's points earlier today, it's very hard to saturate disk I/O with a database. And so there is still room for either virtualizing some nodes or running multiple processes and have them bound to different CPUs, things like that. But what's important about these single nodes is they are what actually hold the real data. The config servers and the Mongo S's hold the config servers hold a very small amount of data. The Mongo S's hold zero data. And so what happens is the Mongo S literally goes, hey, I need to find this piece of data, and then sends it to the specific node to ask for that. Now, if it's asking for multiple pieces of data, it's going to aggregate that in the Mongo S. So you need to be careful in your design pattern to avoid it having too small of a footprint of memory, or your Mongo S is going to OOM and it's going to look like the database is just repetitively going away. The other thing that these do is journaling. If you're using different engines, such as WireTiger, it has its own journaling mechanism compared to the MemMap designations. And so you just make sure you read up on the engine and how you're using it, because, for example, WireTiger has an optional journal. You actually don't need it to stay consistent. And that's a very important caveat, but it does guarantee you won't lose any data ever, as opposed to you might lose a couple seconds of data, but your database won't become corrupt. So it's not like the old days in my ISAM where if your database server crashed, you had to go do a recovery of my ISAM. The recovery record's there, but it's more like if you're not forcing syncing on a regular basis, there's a small amount of room for data loss. And it's very similar to a MySQL node where no replication is being used because it is standalone. The second that we move to a replica set, we end up provisioning 10% of our free disk space as our oplog. And the oplog you can think of as being very similar to a binary log. It's pretty much the exact same thing. And in fact, it's most akin to statement-based replication, because what it is it's a timestamp and an object that I'm updating, deleting, or inserting, and then the payload of what I'm doing to it. So in the case of an update, it's going to be something like I'm updating object 1, I'm setting field X to be value 99. What's important here is it's not storing the like an incrementer or a decrementer value there. It's storing the final value that it should be, because one of the special things about Mongo is it's completely idempotent. So if I started a backup at 12 o'clock, at 11:55, I could replay my replication from 11:55 all the way to 1 o'clock, and I would get to 1 o'clock without having collisions that you would expect to see in MySQL's replication system. But as far as replica sets go, those are just members of a logical member of a group, and they all replicate to each other, but they all also have some HA componentry to them to allow them to just to fail over. And a lot of what you've been seeing in MySQL with global transaction IDs and MHA is just built into the core of the system, and it'll do it for you. And one of the biggest benefits of this is the auto healing capability. If you have a secondary that runs out of disk space for a prolonged amount of time and then it comes back up, the Mongo system can actually detect that it wouldn't ever be able to catch up and start an initial sync for you. Where in the MySQL world, you would be paging out to a DBA. The DBA would need to restore or rsync or do something to get that data back working. The other thing that Replica Sets can do for you is you can actually have different indexes on different ones. And I'll talk about that here in a little bit more with some of the tagging and stuff it can do. And then sharding in all is really just, you have a group of Mongo nodes that make up a replica set, and each shard is a replica set. It's just another name for a replica set. And at the sharding layer, you just have metadata that says, this shard owns this piece of data, or this shard owns everything for this database that isn't sharded, is the two paradigms. And in that, what you have is, in the config servers, what you have is on the replica set's primary, it will actually go to the config servers and pull the records that it should own. And the benefit is if there's a balancing action occurring on the system, when you query that data, the duplicated data that might exist in two locations at that exact second will be filtered out, so you get only the real data that you should be seeing to remove that duplication effect. Let's see. Most of the legwork is actually done on each individual shard. So the primary of shard 1 and the primary of shard 2, when we're talking about balancing, what's actually happening is the Mongo S acts as a coordinator and says, shard 1, move this range of data to shard 2. And then shard 1 starts copying that data. Shard 2, once it's received that, notifies it saying, I have all this data. And then shard 1 reports back up, hey, I've copied that data there. I'm going to delete the old records that I don't need on myself anymore. And the config servers in MongoOS update the metadata, so all the queries and all the writes for that range start going to the new location. And that's all in a very atomic way, so you don't end up with like one write going here and one write going there. And then the config server, I talked about the metadata, but in a high level, you have databases, you have collections, you have chunks, a changelog, a lock manager, and a MongoOS list. So the database literally holds a record that says, this is this database name, and primary is on a given shard. And that's to say that anytime I haven't sharded a collection and I just make a new collection for that database, I know that it will always exist on shard 1. And then I could shard, collection foo, and then half of the records would be on shard 1 and half the records would be on shard 2. But if I then created foo2 and I didn't think to shard it, I would run into a bigger problem because it wouldn't be where I expected it to be. Collections, in turn, are when you've sharded something, there's going to be a key there that says key : whatever the shard key you used. And so what it uses there is it tells it, oh, I can check if I'm sharded in the database collection, then I can check in the collections collection if it's sharded, and then that tells me to go to the chunks collection. And a chunk is it's just a logical structure. It's not a physical structure in the system where it's going to say it has an ID value, the last time it was modified, its minimum value and its maximum value, which could be a document and it could be several fields if you were using some sort of compound index. And it's also going to say what shard that lives on. And that is what a balancing action changes. And it literally just changes the shard value to say, I now live over on this other location, and updates all the MongoOS's memory. The lock manager is a little bit different because that helps it know that, hey, I'm currently doing a migration of data, so don't let another migration on a different MongoOS start so that it doesn't have to have conflicts there. The changelog is just literally what it sounds like, a history of everything that's changed on the cluster, so you can use it to say, oh, I see where a migration started. I see that I was moving data and it timed out and then it failed and then it tried to do it again 50 times. Okay, let me go figure out what's wrong with this one shard because it keeps failing on those migrations. And then last is the MongoOS list, which is literally a list of every single MongoOS that has talked to these config servers and when they last checked in, what version it was on. And so it really helps you understand if you have some dev that's spun up a rogue MongoOS somewhere to explain why your production cluster just changed in some way. So the MongoOS itself is responsible for any shard commands. There's several commands. There's like a command called sh status, and that literally tells you what collections I have that have sharded, how many chunks they each have, what databases exist, what version am I on, things like that to kind of give you an idea of what the status of the overall cluster is as compared to db.server status, which is more like NODB status or something like that to give me the understanding of the specific node. And the MongoOS is responsible for doing the splitting or acting as the coordinator for all migrations. It also is responsible for grouping and sorting if you're not using an index and you're asking a question of multiple shards. Like you have user IDs in a range and you're trying to find those and it ends up going to all your nodes. But then you try to sort them based on, the user role, which you never thought to index. Well, if you had millions of those, all million documents would have to be uploaded into memory on the MongoOS, and then it'd have to be sorted, and then you could start returning those results. And that's where people usually run into memory problems with their MongoOSs. So getting into how the oplog works and how replication works itself. So it's basically almost identical to a MySQL binary log, except it's stored in a collection, so in a table rather than in a separate file. And it's a capped collection, which if you're not too familiar with Mongo, a capped collection is just basically a circular buffer. So you've set it to a certain size, like say 100 megabytes. And in the second you've reached 100 megabytes, the next time you insert, the insert will be at the beginning of those 100 megabytes. And it just keeps a marker of where it inserted last, so it can just keep going around in a circle. There's a lot of benefits to this in Mongo because there's when you're sorting, there's a special key called $natural. So you can get the oldest record or the newest record without having to have an index on some sort of timestamp field. So I mentioned earlier it is statement-based replication, but it's idempotent statement-based replication. So you don't worry about transaction IDs. You do worry about making sure all your nodes are using NTP. If they're not using NTP, the timestamp, which is what Mongo uses to order all of this, could be in conflict, because on one node, the timestamp was, 1, 2, 3, 4, but on the other node, when it received it, it changed it to 1, 2, 3, 5, because there was some amount of timestamp drift. And then, in theory, you could run into some situations where if you're restoring a backup of an oplog to a certain position, you're one item less than what you expected, and so you have data loss where you expected a point-in-time recovery. So just remember, timestamps become very important in Mongo. This is a good one. And back in the days of statement-based replication in MySQL, if you updated a whole table setting some value, you would end up with a flurry of binary log entries that would cause replication to fall behind. Mongo is susceptible to the exact same problem, except Mongo doesn't have a row-based replication to circumvent that problem. So just be aware that if you know you're going to do a batch job, consider looking at how long your oplog is good for, so that you can make sure that you can absorb that without having your backup strategy be risked. And then if an event occurs right after that, you would have data loss and you would not be able to roll forward because you wouldn't have the oplog to do so. MySQL, Mongo has journaling just like MySQL. It's got journal files instead of IB log files, but they effectively work in the same way, where it's using an LSN and all that kind of stuff. The difference is some engines use it and some engines don't. Well, all engines are forced to use it in MySQL. And the reason some engines don't use it is because they can have separate threads in their own system to do different checkpointing. And in the case of like an LSM structure, journaling doesn't make any sense because it's already an append-only file system, a copy on write files, not file system, but data structure. And so it doesn't care about journaling because it's doing that right in that location. It's not having to do rewrites and moves and things like that. So how replication actually works is not something that I love right now, and I want to see it get improved, but it's just another connection. So if you run into your maximum connection limits, a couple things will happen with a replica set. First, your replication will lag. You won't be able to get additional entries. But more than that, it is very highly probable that the heartbeating of your replica set will fail, and you will lose your primary, and you will go into a degraded state. And so a lot of people like to make sure that they keep at least a 20% buffer on their connections, but I suggest you keep at least a 50% buffer on connections. And the reason for that is if all your apps suddenly disconnect and try to reconnect, you want to have enough room to allow for that to occur. The other thing about it is there's no SQL versus IO thread like MySQL has, because it's not prefetching into files to create relay logs. What's happening is it processes some entries and then it gets the next batch from the primary server and then tries to apply those and gets the next batch. It does this through something called a tailable cursor. So it's like, imagine you did select star from table, but you had a special option that said, once I consume everything I know about, I'm just going to keep checking to see if there's new records that have been added to the end. That is basically what a tailable cursor is. So think of it as a cursor that becomes position aware and can continue on even though when it first requested its query, that data didn't exist. This is something that doesn't exist in MySQL because, well, it's ACID compliant, and this is very not ACID compliant in its nature. The other thing I would say is there's sometimes some performance degradations when people start trying to use the oplog to like write data from your Mongo cluster to a Hadoop cluster or an Elastic, because there's no index on a timestamp. And so you end up having to scan all of the records in the oplog up to the position you were at last if a process dies or restarts. The reason this is important is if you make your oplog really, really large, like 200 gigs, this is going to become a very large problem because it's going to push everything out of your hot cache of memory, and you're going to run into like these horrible performance problems if those types of processes stop and restart. So it's always more beneficial to have more processes on a Mongo node, so that each oplog is smaller to avoid some of that behavior if you need that kind of scale. Most people, I would say 20 to 30 gigs will hold 2 or 3 days in most use cases, sometimes weeks of oplog, depending on how busy your system is. So one of the things we monitor at Percona is the oplog history size. And that is just from the first timestamp in the oplog to the last timestamp in the oplog, how much time is there? Because if it falls below 3 days, I alert on that because I want people to grow that oplog size. For a couple reasons. The first reason is pretty obvious, so that I don't have an immediate gap if a secondary falls behind slightly. But beyond that, if I'm doing a restore and I want to do a point in time restore, I'm going to need that oplog from the system where something went wrong on. And I'm going to want to trim that to the point that the problem started at. And if I don't have enough oplog, I'm not going to be able to do that recovery. But more than that, when I'm doing a restore of the backup, indexes are created sequentially. So if I have hundreds of indexes, it might take me a day to restore my data and a week to restore my indexes. And if I don't have a week of oplog, I'll have done all of that work just to get a node that wasn't actually restored.
When you said the replication is not rule-based and it's statement-based, and suppose on the primary somebody updates the timestamp, and on the secondary there's a lag of say 2 seconds. So what's going to happen?
So that won't affect Mongo, because what happens is it's going to, in the document, let's say we have a last updated on field. In the document, it's going to say, I'm updating document 123. My update object says to set updated on to this timestamp. And so it will set the exact value that it recorded on the primary, not the relative, like it's not going to use like a now function or a sysdate function type thing. It's very declarative on the value that gets set to that document rather than the function that gets applied to the document. So also on Mongo's oplog and the way it works is I talked about the batches, but the size of the batches is not configurable. And so if you're talking about a very large WAN, like US to Australia, US to EU, for example, between different members of your replica set, there's a very high chance replication will not keep up unless you recompile Mongo changing that value. This is one of the things I have on my desired list on our future roadmap of things that I would like to expose as a configuration variable, because I think that is something that we will need more of as people start trying to create geo-disparate replica sets. In lieu of that, what people are doing is geo-aware shards. So you can say all my data for the EU lives on these 2 shards or these 3 shards or however many, and in my EU data center, all the nodes that need to do that replication are there. And that's data locality, and then you'd want a separate data center in Europe to be the DR for that shard, rather than trying to have my US data center be the DR site. This gives you some data locality for query speeds, but also so replication doesn't fall behind. Rollbacks, has anybody heard about rollbacks in Mongo? Okay, so rollback is completely different than what you would think about in a rollback in MySQL. So a rollback in MySQL is, transaction rollback. In Mongo, a rollback is where your primary node took some number of writes and then it crashed and it had not replicated those writes yet to its secondaries. And so while it's down, the 2 secondaries have an election and decide who's the new primary. And then this node comes back up in number of seconds later and it has, let's say, 5 document updates that had not been applied. Mongo will literally take those 5 document updates and shove them into a folder on the disk in a BSON file, and that's all it does with them. You need to go back and resolve those. And this is important because you can completely avoid this. All you have to do is say, I want to write majority. And that will keep basically that takes a quorum number of nodes in the replica set and make sure that it exists there so that if one node dies, the majority of the nodes had the data. So one of those 2 nodes or 3 nodes or however many make up quorum that are still alive will be the node that gets selected as a primary, and you won't have this issue. And this is kind of a big tenet when it comes to Mongo in general, is it's not a matter of it's not consistent or it has data loss or things like that. It's that you can choose to allow for data loss, or you can choose to not allow for data loss, depending on your use case. Because some people using Mongo treat it as a transient store, while other people treat it as a persistent store. So a couple key things that you can do in Mongo that are more interesting to me. The delayed secondary is probably one of the most interesting ones. So I can literally just say, I want this secondary to always be an hour behind everything else. And when you have that, you can say, instead of, I had some event where I deleted a collection accidentally. Well, instead of having that whole recovery process I was talking about, you could bring down the entire cluster, rsync that one secondary to all the other nodes, start everything back up, and you're back in a working order from an hour ago. And that oplog on that old secondary is still there. So you could restore any extra data that it might have on it, or you could actually go in and before you delete those other nodes, restore those so you could get to that point in time. But the most important part is it's not a backup strategy, but it is a remediation to prevent having to do a full restore of your system. If you're using a delayed secondary, by default, it's a hidden node. What a hidden node really means is if I do a normal db.foo.find query, it will not use that node to answer the query. And this is important to prevent those delayed secondaries from giving you some really stale data that your app isn't expecting to be stale. What you can use to get to that node specifically, if you want to say do backups against those delayed secondaries, so there's no way my backup is affecting production, for example, then you can use tags so that when you do the query, you can say, I'm querying with this write concern of this tag so that it knows that it can go to that specific node with that specific tag. I mentioned earlier that you can have different indexes on different nodes on secondaries. Tags are how you do that, but it becomes very manual because you have to build a secondary, add it to the set, make it hidden, and then you have to add the tag to it, and then you have to go to that node and make it a standalone node temporarily, add the indexes you want, add it back into the cluster again. And then at that point, it would answer just for that. And if you say you had a query, you could say tag that query to say this type of query should go to this node because I know its indexes are optimal for it. And in some very large cases, people are doing this so that the primary node has no indexes whatsoever on it, and all the secondaries are going to different nodes. And so they can have this whole farm of read slaves effectively that are all optimized for different workload patterns. And this helps them use smaller amounts of memory but still have 100% index coverages. Chain replication is another, it's a feature of, but it's could be a problematic feature for you. So you need to be careful about turning it on. But in chain replication, this says a secondary can replicate from another secondary in the same way MySQL has some of these abilities. But in the same way that in MySQL that increases latency, in Mongo that can increase it as well. And in a replica set where, let's say I had a replica set where I had 3 nodes in America, a node in Europe, and a node in Australia. If for some reason the node in Australia had some sort of hiccup and couldn't see there were 2 nodes in the US, and there was a primary node and then there's the secondary node in the EU, if you had chain enabled, it might select the EU node to where you have the latency from the US to the EU and then the latency from the EU to Australia. And all of a sudden, Australia is going to fall way behind. And so it's good if you have geo-local things to use chain replication because that takes pressure off of your primaries, but don't enable it if you're running really far spread, high latency type replica sets. So I talked already on the config server, but in the changelog, I didn't really go into what changes are recorded. So normally it's just splits and moves. A split is where a Mongo S has received a whole bunch of bytes for a given chunk. It knows that a whole bunch of deletes or inserts or updates have occurred there. And so it will trigger a logical request to say, how big is this chunk on the physical data? And then it passes back to it and says, okay, I know that the middle point is 10,000 for this ID. So I'm going to split on 10,000. And now where I had one check from 0 to 2,000, 0 to 20,000, item 10,000 is the middle spot. So now I have 2 chunks, 0 to 10,000, 10,001 to 20,000. And this is not touching any data. What this is doing is increasing the chunk count on that specific shard. Then the balancer would kick in and use the move chunk, which would donate the data from one shard to another shard and then clean itself up and do the balancing actions I talked about earlier. Other things that Changelog could have, however, are if you've dropped a database, if you've created a database, if you've sharded a collection, those will show up in that changelog as well. More times out of not, what I'm looking for are specific steps in the changelog. So what you'll have is like a document that says it's a move chunk dot start, for example. And it will have details, and in those details there will be steps 1 through 6. And there's I have on my LinkedIn SlideShare, I have a talk that's all about the balancer. But in those steps, there's different phases like getting a metadata log, making sure things are consistent, making sure a split hasn't occurred since I started trying to balance it, things like that before it starts moving data. And then finally, step 6 is where it deletes the old data. And so if you have step 1, 2, and 3 done, and 4 isn't there, I failed to even start copying data to my destination shard. If 4 is there, but it's 24 hours and then step 5 is not there, then that's telling you that I actually was trying to copy to that destination shard, but it was so busy after 24 hours, I couldn't do that. And there's a special timeout in move chunk in Mongo that says, if I've tried to move this chunk for 24 hours, give up and let me try to balance something else, because obviously this is way too busy, or that shard is way too hot with a write lock, or something else is going on. And so I talked about the chunks a fair bit. So they're just a logical range. It's not physical. And it lives in config.chunk. So if you log into a Mongo S and you literally just use the config database, you can say db.chunks.find to look at those chunks, to see how that stuff's broken down. And actually, when you're running sh.status, that is literally doing some queries for you. So I recommend, if you're newish to Mongo, run sh.status without parentheses, and you can see all the things that are being done to generate that report for you, because that will help you understand how you might start auditing your system a little bit more. Orphans are an interesting problem in Mongo. There is a command that says clean up orphans. I personally am not a fan of this command, and I don't run it myself because it does not have a read-only mode. So I literally have to run this command and let it clean up orphans and cross my finger and hope that it didn't delete all of my data, which is not optimal for obvious reasons. There's some open source tools out there that will let you scan for them with JavaScript or Python, but the cleanup orphans is the only one that will actually clean it up safely. So you could do some other scripts to do read-only. But what an orphan is when I was talking about where you donate data from one shard to another, and then your original shard cleans up that data. Well, what happens if that cleanup fails? There's a couple error modes that can occur in Mongo depending on the version. So in 2.4 and before, there was this flag that was called wait for delete, and that was set to true. And what that meant is I am not going to allow any other balancing actions until I've deleted all of the documents that were there. In 2.6, what they did is they added a new queuing kind of logic to it that said, I'm going to write all the document IDs that I need to delete into this queue and let another thread clean them up kind of silently for me. The problem with that is it's not a persistent queue. And therefore, if you have an election, you will lose that scope and these orphans will be created. But like I said earlier, there's a chunk manager process that filters out things that I shouldn't own, so it will hide it from me. But not if I'm reading from secondaries. Only if I'm reading from the primary does that kick in. And so if you're reading from secondaries, your counts can be off. And this is a natural and expected behavior for eventual consistency. You are expected to run this tool on a regular basis if you think you're creating orphans. There is talk about automating this, but until I see a report that says that reports how many orphans you have, I don't know how quickly Mongo is going to actually start adding that automation into place. I personally have a different viewpoint. I don't think you should be cleaning this type of thing up after the fact, because again, reads on secondaries are basically incorrect, depending on your point of view. And so I prefer to see what we can do about trying to prevent the orphans from ever occurring in the first place. And we'll see what Percona or other tools that I might publish on Percona Lab in the next 6 months, a year, will do to help manage this stuff more effectively. So that's basically how replication works. And in replication, when you're doing sharding, there will be special flags set on deletes in the op log that will tell it that this was a delete that occurred because I was balancing something off. So depending on how you're using the op log, you might filter that out so that you don't accidentally delete it from some other database technology you're replicating what you've done in Mongo to. But I think it's important to understand that those flags do exist, so you should read up on that or find me at the Percona booth and I can explain them more. But picking a shard key, there's some very poignant rules that you should follow. Some of these are in the Mongo manual and some of them aren't. It needs to be immutable. If you try to change the value that you've picked for a shard key, it will error, and so you literally have to delete that record and recreate it to be able to change that value. The problem with this is if you're doing that a lot and the old values that you've deleted are say they're very low in a number sequence, you could end up with lots of chunks in the cluster that have 0 documents in them, which will confuse the balancer because you have some documents that have 20,000 or 100,000 or 200,000 documents in it, and then you have these other chunks that have 0. And statistically speaking, that should be spread evenly, but logically speaking, it's very probable at some point your cluster would have a whole bunch of these 0 chunks that exist. Mongo in 3.0 added a feature called merge chunk so that if you do have those and they are sequential, you can run that command to clean it up. You can read up on it. I don't know a lot of people that use that command very often, so I've used it. I know that it's safe, but I wouldn't advocate anybody else using it unless you've really researched what it's doing and make sure you understand what you're doing to the cluster, because the restores of a clustered setup are a little painful because it's a distributed system. The other thing is you should not be using fully non-unique values, because if what you have is like say you have a boolean and you want to put that in your shard key, what's going to happen is you might have 50 million documents that say this boolean is no, and without secondary fields in a compound index, then you will not be able to split that data, and therefore the system will not be able to balance, and you've ruined half of the reason a lot of people are using Mongo, which is the balancing aspect and the HA aspects. That said, on the opposite end of the spectrum, you don't necessarily want monotomically increasing values, which an object ID is monotomically increasing because the front part of it is an epoch time. And therefore, it has to contend with this. And so if you're using IDs or dates or things like that you need to shard on, you might consider a hash shard key, because the hash shard key will guarantee they are spread evenly across the cluster rather than having those hotspots. The other thing is you can use text fields as a shard key. However, even Mongo, when it did the hash shard key, which is basically an MD5 of any value, does not use the MD5 for the actual shard ranges, or chunk ranges, I should say. What it does is it converts a big portion, but not all of the MD5, into an int64 number, and it uses those ranges so it can do better math calculations when it's moving the data around. Text you can do. However, the longer the text is, the longer the shard key itself is, and the more memory on the Mongo S is needed to load that index into memory to figure out where to route the data, and the longer it takes to route that data. And so it has a compounding effect on you. And so I just would avoid text fields, or at least use truncated text fields that are of a very specific limit so that you know they always have a consistent behavior. And the final one is, if you are using a unique field, those fields must be on the left side of your shard key. So let's say I have a unique user ID. I could not say, user type, user ID. I would have to say user ID, type for my shard key, or the system itself will reject it. And the reason this exists is indexes, while they might exist on individual nodes, if you're using a unique and you're using it as in a sharded environment, the shard needs to be aware of that, and the cluster needs to be aware of that. Otherwise, it can't guarantee that uniqueness across multiple nodes. So,
but what that means is that every query which is going must have both the fields of the shard key.
Say that again?
ID plus type.
Yeah. Well, no. Actually, if you're with a shard key, you don't have to use all the fields of a shard key in a query. You can if you're using multiple fields like that, and you have a user ID lookup because you want to find that one user's record, and you don't know the type yet. Just query on the user ID, and it will use as much of the shard key as possible to route that query. And so in the case of like a user ID like that, where the one user ID might have multiple types, they're probably all on the same shard. But it could be that it's split exactly on that point where it ends up going to two shards for the different types. Yeah, it might do a scatter gather, but I don't consider that a bad scatter gather, because everybody talks about how bad scatter gathers are because it has to query all the nodes and then collect all the data again. But if you're only hitting two nodes, I would call that a reasonable scatter gather, because it's not that impactful in two nodes. If you have 30 shards and you're querying all 30 shards for a piece of data, you've really killed a lot of your performance because you're only as fast as the slowest or the most locked one of those other shards. If you're only doing two, then your probability of being affected worse than that one node having been heavily loaded is fairly small. So I talked already on the changelog on how it does balances and splits and drops collections and new sharding. This is probably the most important collection in the config server to watch after the chunks collection, because this you can actually do a lot of neat aggregations on to say, how many chunk balances or splits did I do in the last hour? And then you can graph that so you can see if all of a sudden some behavior spiked, and you can go, oh, well, 3 hours ago we released a new version of the product, and 3 hours and 20 minutes ago I saw that it spiked a huge amount in the number of splits that were occurring. Did we do something we didn't expect in our data? The locks helps you understand not just what is currently running, because there's a state field for each entry in the locks database. If it's 0, that means it's unlocked. If it's like 1 or 2 or something like that, that means it's currently locked or doing something. And so you can actually, and it has a timestamp of the last time it was updated. So you can say, oh, I was doing a migration yesterday at 3 o'clock. Well, that's the last time I did a migration. That helps you understand what was going on in the system at a previous time. But remember, it can have locks that are no longer present. So just because an entry exists in that collection does not mean that it's a current lock held by the system. Make sure you check that state level. One thing to say about looking at Mongo logs in general, if you are sharded, you need to look at all of the primary logs and all of the Mongo S logs, because any Mongo S could be the balancer at any time. And because the work for balancing is done on individual shards, you need to look at those logs if that erred in some way. I can't just look at the Mongo S log and find out what happened with the balance that went bad. So if you notice your system is not balancing, sometimes you want to turn off the balancer and run a command called sh.movechunk and just select the chunk that's on that specific shard from the chunks collection to move it manually. Because if you try to move the same chunk that kept failing, when you run this command in a user context, it will tell you what the error is. And then at that point, you can go to Google user forums, MongoDB support, Percona support, whoever you're using for a support vendor, and say, hey, this is happening. Can you tell me how we can deal with this? And people can get back to you. One of the common things that can occur there is something called a jumbo chunk, which is defined as being more than 64 megs in size or having more than 250,000 documents in it. And it will refuse to balance a chunk of that size. What the balancer should do, and does most of the time, is try to balance that, notice it's too large, and issue a split, and then the next balancing round, it will then move that split version of it. However, like I said earlier, if your cardinality is so low that it can't find a split point for that document, it can't break it apart, and therefore it won't solve that problem. And the sh move chunk and running split commands manually will help you understand that problem exists. I suggest you look up sh move chunk. You can literally just type it into Google, type sh.movechunk space MongoDB. It'll take you right to the manual page on it. And on that page, there's a link to the actual move chunk command to explain how if you were running it as a run command instead of a helper command, how it works and what it's doing. And there's some very interesting features that you can use with it. And depending if you're using hash sharding or a normal forward-backward type of index, then you need to operate that command slightly differently. That said, jumbos are also painful if you're trying to scale down a cluster. So let's say we launched, we were really big, we became less popular. I wanted to cut my inventory by 50%. In that type of setup, there's a command in Mongo called a drain shard. Or is it remove shard? I can't remember if it's remove or drain shard. But when you run that, what it does is it tells it to start moving chunks off of that. And you can keep running it several times to kind of get a status to understand how many are left. The problem with this command is it tries to do them in a sequential order. So if you run into a jumbo chunk, it'll get stuck there. And so you might want to stop the draining and then manually try to remove those shards off of that chunk with sh move chunk so that you could see the error on what went wrong. Typically, I don't use drain shard. I use move chunk so that I have a greater level of control and I can add pauses in between. I can make it check the load on systems, all sorts of stuff like that, to make it drain as fast as possible without affecting production, rather than remove shard will run it as fast as it can and have a higher chance of affecting production. Let's see, move chunk. Also, the other thing is, I talked about this earlier, where Mongo S does split chunks based on how much bytes it thinks it's written to a chunk. This is not persistent understanding for the Mongo S. Each Mongo S is isolated from the other Mongo S's and only holds its data since the last time it restarted. So to this point, if you're having a problem with a Mongo S, you should try to run a command called flush router config rather than restart that Mongo S. Because flush router config will flush the config and get a new version of the config, but it won't lose that context of what's been written. So if you have a regular process that's restarting Mongo S's on app hosts, you could easily create these jumbo chunks because not a single Mongo S has not been able to see enough writes at any time to know that it should trigger a split. To this point, when I was at ObjectRocket, I wrote some tools. You can look at github.com/ObjectRocket utilities. And in there's a chunk hunter, a chunk splitter, and a chunk manager script that you can actually run on the system, and it will measure all their sizes, and it will recursively split jumbo chunks for you if it can. And so that's a good way to help clean up. I'm probably going to write something more daemonized and more official into the Percona toolkit at some point soon. I'm just trying to figure out, does that belong in the official toolkit, or is that going to be just a side script that we keep on Percona Labs? So I talked earlier about the stages, and so I put this in this slide deck because we are going to share these slide decks out after this conference. But I talked about the phases 1, 2, 3, 4, 5, and 6. What actually is happening is in the first phase, it is just parsing the requests and then preparing for that, making sure nothing else is running that should block it. Then it goes to the config servers and activates one of those migration locks in the locks collection to say, nobody else tried to do a migration, I'm about to do a migration. And then it goes and it goes to the donor node and it gets all the documents it needs, and it goes and it sorts their block list so it knows how to get to those documents as quickly as possible. And the reason it needs to do that is Mongo does not have a concept of a clustered index. So the data on disk is pretty much completely random. And so it needs that ordering to copy fast. Then the fourth phase is where it's actually copying the data from the donor node to the destination node. At this point, there's been no change to the config servers themselves. When that process is done, it will take a global log of the config servers, and it will change the changelog, and it will update the chunk. At that point, it also updates the version. It's called a config version, which is exposed a little bit more in 3.2 than it was previously. And that will tell the Mongo S's that they need to get a new copy of the map so that they now know where it lives. And so the second one of those tries to do a write, it will detect that. Also, if that node has been, let's say you're mostly a read system, if that node hasn't checked in for a very long time with a write, it will actually resync that on an automatic basis as well. So there's two ways that Mongo makes sure the config is in sync. But then after it's done that is when it gets into the cleanup phase. And I put a star by that because that's what I was talking about with the wait for delete versus the queue deletes that occur. And so that cleanup can run in a couple different ways. And you can actually control this, by the way, in config.settings in a Mongo S. You can set wait for delete or secondary throttle and a chunk size and a few other things like that. Some of it's well documented, some of it's not so well documented, to control the behavior of these balancing actions. I don't suggest you change that unless you've been given direction on you're having this problem and either Percona or Mongo or a user group is telling you to change it to get around that problem. Because otherwise, you're running into different scenarios that may or may not be as tested on your version. But that's a high level of like all the componentry of what happens in Mongo S for sharding, some basic rules on what you should consider, but then also how replication works. And so kind of the recap on that would be, it's basically statement-based replication if you're coming from a MySQL world, but the big difference is the SQL thread and the IO thread are one single thing in Mongo, and it's just a normal client connection, so it can be blocked by other connections. And so connections become very important. Slave lag becomes very important in your monitoring of your cluster. Does anybody have any questions for anything?
So with respect to the shard key, let's say when we have multiple columns in MySQL schema, you may have multiple columns on these Euclid indexes. And what is the best possible way to do that with the sharding, to create a separate collection with each of these indexes as the primary key or shard key?
Well, I mean,
your query may come with, say, directly indexed column, not with the shard column. Sharded key may not be a first column, may not be the part of every query.
Well, so the shard key doesn't have to be in every query. That's just where you scatter gather. And so I wouldn't use different collections in that case. The only time I would use different collections is if I had different data sets, or maybe I'm even duplicating my data so that I can improve access patterns. But I don't think I've ever really seen a case where people were doing collection duplication rather than trying to pick the shard key that handles most of the queries well. Because what I do when I'm analyzing a shard key, to pick a shard key, I actually go to the business and I go, okay, what do you think you're doing to this database first? And then I go and I turn on the profile in full mode and I record everything for 24 hours. Then I go and I look at all the queries they've done and how they've been patterned. And then I go, actually, 80% of your use case is this, and 20% is this, or 60, 20, 20, or however the breakdown is. And then I go, if we use this prefix on the shard key, I can cover these 5 patterns, and then I only leave these 2 patterns. Now explain to me what these patterns are and what their criticality to the customers are, so I can determine whether or not I need to rethink that shard key based on asynchronous versus synchronous processes in your system. Because if I have a million things occurring in the system doing scatter gathers, but they're all asynchronous processes that are very short-lived, I don't care about those really. I care about these 3 other query patterns that literally I want to make those as fast as possible to help with the user version, a user view of my system's responses. And so there's a lot of times where I'll go in and I'll look at it and I'll be like, okay, I know this is counterintuitive, but shard it on this because this will cover the use cases for your customers, not your reporting, because there's the expected logic is reporting takes longer than a website interaction. And so you want to align to that. And so that would be the single biggest thing I say about picking a shard key outside of those rules is first measure what you're doing, and then secondly, prioritize those based on the client SLA, not some internal SLA of I want reports to be this fast or I want asynchronous process to be this fast, but actually like what is measurable on the success or failure of my product. And that is why you make the decisions with sharding. Anything else? All right. Well, thank you all.